So I'm going to start by revising these three words. Everything written there is something that we already saw from Wednesday. But we were on our way to prove that the spherical maximal function is Laguna diversion is bounded from H1 to H1. And we are following here approved by Jim and Andreas, in which they simplify the previous existing proofs. It actually also holds in greater generality, because we are not only, we can consider actually any compact, any border metal compact is supported, okay, that satisfies properties 1 and 2. And remember what 1 and 2 are saying. 1 is saying that for some P sufficiently close to 1, we have good smoothing properties for our measure, okay? I think I'm gonna talk a little bit more later about property 1, so that it's not more clear. And 2 is a covering condition for the support of the measure. Okay. From now on, let's just focus on the case of the sphere. Okay. So remember that we saw that for the sphere, we saw that by Plancherel. We are getting here the decay of the spherical, very transformed spherical measure is d minus 1 over 2. Right? But here we are in that 2. So that n that I wrote over there is d minus 1. Right? D minus 1 happens to be the dimension of also the sphere. So we are going to need delta to the minus d minus 1 delta rolls to over the sphere, right? Which is condition 2. So condition 1 and 2 are satisfied. So essentially, whether we have here into a neighborhood, a delta neighborhood of manifold which has a certain dimension, if we have for a certain P, that we can get a smoothing for that dimension, then we are good, right? Yeah. Okay, so in that case, we have the H1 to get our coordinates. And we are using this atomic decomposition formed by square functions. Okay, which I didn't show how to construct it, but I just stated the summary of the properties. So the benefit of using the atomic decomposition through square functions is that it tells us what is the structure of the atoms in terms of the frequency decomposition. Okay, so that the atom then is layered up by a certain building blocks, right? And the building blocks, they are functions which we can think of them as being essentially fully localized at the scales which are reciprocals to the inverse frequencies which are higher than the reciprocal to the inverse of the segment. Okay. And we can put together the H1 norm by the norm for the. So then we want to show that these Winkel inequality holds, right? And then we try to implement the classical ideas that one does in Calderon-Simon theory. One of them, if the operator is local, then maybe we can use some equivalence of the operator, right? And that's what we did when we split these two parts, right? So we split the atoms, and here we have this dilation K, right? So this means that the measure is has support at the scale 2 to the K. Okay, so if the atoms here, so remember this capital L, it means that the side length of the W is 2 to the L, capital L W. Okay, so then if the K's are smaller than 2 to the L W, then this convolution is not going to amplify the support. Okay, so it's going to stay local. And then we're going to have the other part. Okay. So for the first part, then we apply this property of locality of the operator. Okay, but then we go through L1 in order to apply triangle inequality because I need to do that for fixed W. Okay, the property of being local. Then once I'm in L1, then because it's local, I can go through L2. In L2, apply the volume of the operator, and I can put together the L1 function. Okay. So that was the easy part. Then we have a second part. Which is when these measures they have support which are larger than the atoms involved. Okay, so in this case we are going to try to use cancellation. With cancellation comes in the form of this smoothing property. Okay, so and then we went to that exponent is 0 for which we have current P0 for which we have always hypothesis 1, okay? But you can see in the case of the sphere it's just 2. Okay. And then once we are there, we are going to use the decomposition of the atoms in their frequencies, okay? That the atom is composed by frequencies, because we have here we are working with averaging operators, which we know information about the Fourier transform, right? So we want to exploit the frequency information, right? So this is why this is useful. So so then we have this frequency decomposition, let's say, of the atom, which is the one that we incorporate here. Okay, so here it is. I block my atom in the different frequencies, and I'm also adding here an extra parameter L, which is the silence of the atoms. Okay. Then once I layer up, then I can take the sum, the scale of the frequencies as it goes down. I can take it outside. This is my little n. Okay. And I'm also replacing then the supremum by a little LP0 norm, okay? Because my hypothesis is for no supremum, right? It's for a fixed average. Okay? So, and then I have here something which is looking more, looking like I could apply this to my operator potentially, but I still have here that there are atoms at different scales, okay? So now I use these different little value projections to take the sum outside, find the orthogonality, and now here I can apply my hypothesis. Okay, so that's pretty much where we sort of end it. Okay, where we apply the hypothesis, and here I need to be careful because I need to rescale, right? But this is k, so then the k comes here as a minus k and so on. So then I'm going to get n plus k of w, and it is going to come. And I'm going to use for this field because I just put there an n, and then the n now is back notation for this n, okay? For this little parameter. So if you allow me, I'll just do this here. Okay, d minus 1, and then it's going to be a p0, with respect to the p0, then divided by p0 prime, which is my hypothesis. Okay. And then I have here this is very tiring to try on the board because it's so. But the idea is clear, no? What I picked it up from the other day. Okay, so now in there I would like to now put the atoms together. Okay, so my condition to recover the H1 now. Okay, so then what do we have? So now here I obtain decay into a variable. So the summing end that I have, I can sum it, and that's fine. Okay. So then I have to put together this sum k. Then I'm looking at the sum k, and then the sum here I missed the W's, but I can put now W's as a W. And sum W. Okay. And then I'm going to repeat already of the end. Okay. I'm scaling when I'm about very good. 2 minus 1. Okay, so this one now I've already got the information I wanted from the frequency scales, right? And then the end, sorry, if I want to take it out, if I want to take it out, then I just fix this, okay? And I put already the normal for the guys, okay? Because the inner to norm, they are comparable. And let me assume for a second, if you want to make things simpler, that we are in the case of the sphere, otherwise it's just a plain helper, okay? But then this becomes 2 over 2, so it's a 1 divided over 2. And then the situation of the I get it. Okay, and now remember what was the game that we did. Okay. In the end, I want to sum over this W, which should be a W, in order to recover the H1 norm. Okay. And here I am summing still over all these scales, K, relations, and all the W's. So let me change this. And then I sum over all the K's, greater than the W, and now here I sum over all the W's. Okay. And I would like that this thing over here, this is smaller than this. Okay. And I have here alpha to the P0, okay, which was alpha squared. So I want to end up with just one alpha in the denominator. So I also need here an alpha. Okay. So if I can do that, then I'm good. Okay. So if then this sum okay, well maybe let me put it this way. Let me just break it more. And this K is greater than the LW, so this is a geometrically linear sum. Okay. So in the best case scenario is that when K is above LW, okay, then I don't have this factor, okay, and then this, which I can cancel this here, there shouldn't be two, but I have that if AW is smaller than this, then I'm good. Okay. Because then one of them I can trade it with the other two, and then I can sum the geometric series. So that situation is the good one. Okay. But I might not be always able to do that, right? So if this happens, then I cannot just use that this is bounded by 1. I need to use that this is much smaller to compensate with that loss. Okay? So then I stop here. Second place, depending for each atom, okay, where B greater than W such that 2 to be minus W B minus 1, okay, then this is comparable to with the W 2 is comparable to then in that case I can sum and I can close this argument, right? Okay, so so what does this mean? This means that I still have one term to follow, right? Stopping already. Yeah. So we need to do Now, I will be exactly. I will now take between now W and okay. These are the remaining terms. Okay. Okay. So so now here we are in a situation where the operator is not local, but also the dilation is not super far. I mean, it's not super far, it's not super large, in the sense that I have some condition, I know how large it is, then I can relate it to the norm of the operator. Okay. So in other words, if I have if I just look at mu k convolved with a W, okay, this is here I have a second W, and then the mu k is going to be sphere according to the points, the convolution is going to be supported in this sphere. Okay, so that means that I have here a neighborhood of the sphere where the width of the neighborhood is precisely the scale of the atom. Okay? So so then this is going to be supported, okay, in a sphere in this neighborhood. So let's say in W is going to be e to the k times sphere plus this second support of the W or the 10 W, whatever. So then the measure of this is going to be the sphere to the k, the minus 1, and then times the width of this guy, right? So it's going to be a W. Okay. And that's for a single atom. But here I can have many, right? So I can define my exceptional set to be the sum for all the W's that are here. The union of all these exceptional sets, okay? And then the and the union for that's correct, right? And then this function then is going to be supported in this exceptional set. Okay. So then the measure of this is going to be a measure of it. Okay. So so now this is going to be smaller than these values. Okay. And then I have the k, 1, and this will be another one. Okay, and the biggest possible case is when the k is tau, right? The k is controlled as an upper bound. So now we know this has here a solving condition. So so tau, let me add here minus LW E to the LW. Okay, then this first guy here, I have here the minus D minus 1, so then this is exactly this condition, but with a plus sign. Right? So then with a plus sign, it's going to be this one goes on top and this one's where right? So I apply the definition of tau. Okay, so here I missed a sound without then it's going to be a square and this one will be 90. Then I have to plug in to the L E. Okay. But now this half and this becomes this is not it's basically the other middle. Okay, so the exception, we can throw away the exceptional set that was giving us this information. So, as you can see here, there are the ideas that go in are we see what we've done. Are the one reminiscent of from Calvin theory, you know, so we throw away an exceptional set, which is this one. Okay. Then when the operator is local, we are just going to the values that it already appears in the proof of the Hilbert transform being modeled from H1 to O1, right? And here we are applying cancellation, right? Because we are looking at what happens when we have a frequency and we have a smaller cube, and this the difference of this is the parameter n, right? Which is the gain of the okay. So let me let me perhaps mention just to close this discussion. Okay, so something that at some point I said assume that P0 is equal to 2. Okay, if P0 is not equal to 2, we just do a handler. Yeah? Because what we want is to relate this to the L2 norm of the P0, right? So this is just. So we just do a handler at this step, okay? And then all the power will become everything becomes admissible. And once we are at the level of the 2 is where we use the same stopping time argument. Yeah? It's just an extra step. But and then see that the condition 2 is the condition of the covering is also used there, right? Because this condition 2, that's precisely what appears when we compute the measure of this eta value, right? If so, it's crucial that it's matching the condition of the solver. Yeah, just to conclude, like something about condition 1. This type of estimate is best possible. Okay. In the following sense, so assume that we have an average, okay, and sigma is an n-dimensional surface. Yeah. I'm saying there what does condition 1 mean? So we already discussed that if P were equal to 2, then I could go for branch array, and then I could ask for the scale of the spherical measure to be precisely of that size. No? So on L2, condition 1 is the same as what's this? That's at the L2 level. But this is a very strong condition to ask. Okay? The sphere satisfies it. Yeah. But for instance, if you just take a curve in R3, it already doesn't satisfy a curve in R3 with even which is not degenerate, okay, with curvature and torsion, or in Rn, it already doesn't satisfy it, because in that case, the less decay that one can get is one of the dimensions. Okay. So these averaging operators at the on L2. So the lower is the dimension, with the weaker decay that we are obtaining. They are very similar averages. However, it might still be possible that we can replace the equivalent condition of this. This might not happen. This might not happen at the event level, okay, but we might have substitutes of this. That is that when we are sufficiently close to 1, okay, so this is always an averaging operator, okay? This is always an averaging operator, so in particular it satisfies L1 bounds, okay, with 1. It's not improving, but it satisfies L1 bounds. So then by interpolation here, we will have that satisfies P with P bounds with 2 to the minus J and divided by P prime. Okay. So maybe it's not holding at the L2 level, but close to L1, we have this intermediate improvement in the frequency scale. And what I'm saying is that this quantity that appears here is best possible. Okay, so that's the best possible nature that we can ask here. And we can see this by just testing. Here we want F to be supported with the scale to the J. So we may as well just take a little Belly projection. Okay. So we can little Belly projection on the scale to the J. Yeah. Then what do we want? We want on the one hand lower bounds for this, okay, and then just compute here the normal this. And then if we look at lower bounds for this, then if we just focus on, let's say, X be in a neighborhood at the scale 2 to the minus J, or maybe 2 to the minus J divided by 1,000, okay, by the constant of the manifold that we have here, okay, then what does this mean? This means that then there exists for every X in there, there exists a certain S0 in the support of the, let's say, of the parameterization, okay, such that sigma S0 minus X, this is a small. Divided by whatever I want. Okay. So I can extend this to also to another S, provided the S minus the S0 is also smaller than 2 to the minus J divided by another 1,000. Okay. So in other words, there exists a point S0, okay, around, and there's a ball around it, okay, and it's a n-dimensional ball, okay, for which we have that this that appears here is small, okay. And then if I make it, this is now dilated at the scale to B at the eta J scale, no? So that means if I put here, this is going to be this, and then it looks 18. That's what I take. Okay, so this means that I can make this when it goes to the J here close to the origin. Okay, and then if I have chosen my eta such that close to the origin, is positive, certain than a constant, then I have a lower bound for this quantity. Okay. On this. So then I pick up here this part of the support. Okay, is working now. Okay. So let's see what are the constants we are obtaining. So that means that what points of X am I looking at? Am I looking only at this neighborhood? Okay, so of scale to the range J of an n-dimensional manifold. Okay, so so then what I'm picking up is the codimension, right? So I'm doing B minus n times J, okay, and this is going to be divided by B. Okay. And what am I also picking up there? I'm picking up the 2 to the JB, which is the magnitude that I have for the electric norm of my cutoff. To the J, B. Okay, and then I am picking also the S integration, right? And the S integration was a ball of, and what was the size? It was a ball scaled to the minus J and times the N, which is the dimension of the manifold. So to the minus N B. Okay. Touching the one hand. Okay, then I want this to one side J. What's that? One side J and J, sorry. And then here I would like to have certain exponent, okay? It's going to depend on the P, and it's going to depend on maybe in the dimension, okay? I don't know, J, and then here the normal is, right? These guys were one analyzed, right? So just and we make a mistake, okay? This is J X, the power of E X. So these contact types will be as it is, right? And now here I am integrating this, so I pick up a total of J, D, which comes with the D, right? So okay, and now things should match. Okay. Okay, so I get to the JV on both sides, right? So this seems to go, and then I get here that if I pass everything to the other side, well, here, E minus M, J, I'm not trying to but that it does look right, right? It's cancel the over P's out, and then you've got the N over P, and then you've got the N, which is the end of the P prime, and that's bounded below by the epsilon. The D's cancel out, this one's cancel out, that's what it's, this minus D over JD, minus DJB, they cancel out, okay, now, and I get 2 to the N, J, P, and then 2 to the minus N, J, okay, and this is into the minus MJ, and then there is a 1 minus 1 over B, which is the 1 over B prime, okay, so so this is less possible, okay, so condition 1 is the best natural smoothing that we can ask for. So it's a natural condition. And here, as soon as one has it for a certain P greater than 1, then this actually works.
That's a question.
Yeah.
Is there any known example where you look that there is some LP improvement? Sorry, LP salt level improvement, whatever we call it. Okay, I don't care about how quantified it is.
Yeah.
But this doesn't hold.
The doesn't hold, you mean the H1 to the 1 elements?
No, the condition 1 doesn't hold. Because somehow, like, I think most of the results say that you get this, but the range of P you get it for gets smaller.
Yeah, there's more that's closer to
But
1.
we only need it for some P near 1.
Yeah.
But I don't know why the example. I think all the finite time curves satisfy this conditions, right? Is that right?
For P large enough, I think they do it, right? For P large enough, for P small enough, because
Yeah.
they have a range. Yeah. So of course, there's a dual condition. You know, this is a Fourier multiplier, right? That's a joint. So also you can man Jn over P when P is referred to, right? Sometimes it is difficult. I don't know if I have any example in which this is.
So what's the question?
Is there an example of well, okay, obviously we have something flat, it doesn't have any LP sublevel improvement, okay? Let's assume it has some LP sublevel improvement, non-quantified.
For something odd.
For some P naught, for some exponent, it doesn't have to be.
You want to know if it has it for all exponents.
That it has this, which is just for some exponent near L1. I don't know any example where you have. So the point is, this has to be quantified in a specific way, right? It has to have this one of the P naught prime, like, it has to be this in this Sobolev space with one of the P prime derivatives or whatever, or any of the P prime derivatives. But I don't know an example where you get some LP improvement that doesn't give you that quantified thing near L1.
Yeah, there might be some general results that would say that there are no such examples. I mean, that might be a guess because there are these results, for instance, suppose you have a measure and you have like some P naught that has some that maps to L Q naught for some Q naught bigger than Q naught, some constant. Then in fact, you can always show that for every P, there is a Q strictly bigger that you can still be equivalent with constant 1.
But the problem is that this has to be quantified in a specific way.
Yeah. It's a different question. I realize but there are these results that allow you to go from 1 to everything.
I mean, somehow I think it's quite hard to get it with this sharp P dependence. But every example I know where you've got some LP great.
I have that way.
I mean, LP sublevel.
For the conclusion, for the grade. If you don't know. Okay, so I went lower than what I thought I was going to be, but well, hopefully now this condition is also makes sense what that means in the theory. It's important. And so to wrap up the course, I want to. So what have we seen so far? We saw the proof of Stein's theorem in dimensions referring to 3, and then we saw the equivalence of the Lacunari spherical maximal function for P greater than 1, and there were already ideas of Calderon that came up, right? And we've seen that for this atomic endpoint, also these sort of ideas also come up, right? So Calderon's ideas in this context, and I want to give a final example in which also these ideas they come up again. Okay, I won't have time to do it in detail, so I just want to sketch it. And this example here. So far, we have seen examples when P is close to 1, right? And then we saw calculation theory and the H1 technique. Then what happens if we were in a situation where the P is large? Okay? Then the P is greater than 2 and it's on the other side. So in there, what we will use is the Pfeffer-Manstein sharp maximal function PMO rather than H1. So which is the dual technique, but it's still the idea that come up. Yeah, essentially the same. And I chose them as an example to exemplify the variation, no? Because we had last week the course by Tomek, in which he talked about bit of length. Okay, remember that sequence a sequence A indexed by a parameter T, then you will find the variation of the semi-norm as being the supreme or non-reducible partitions. And then the little L norm of the difference between consecutive points in the mathematician. Okay. So we can apply this to the context of spherical averages, right? So spherical averages, they will have here the parameter T, okay? And so far, we have been taking a sub in T, okay? So we may as well take, instead of the sub, we take the variation norm, okay? And I'm gonna put here now B are 0 and infinity, okay? And I'm gonna call this B are a infinity, okay? Instead of the maximum. This was introduced in this context of spherical averages by Jones, Seager, and Wright, and they studied the properties for the governance, okay? And so things are the following. Okay. And here what is this? So they obtain the following boundedness, okay? It's a bounded whenever these conditions happen, and what are these conditions, right? So first we have a condition that appears here, which is R greater than 2. And we already saw in Tomek's course that this R greater than 2 is a natural condition when we consider variation that comes up, okay? And he actually proved that it cannot go beyond R equal to 2. R equal to 2 and below in this Lagrange inequality for matrix. Okay, so this is a natural condition where we consider the global parameter. Okay. Then there is the period that D over D minus 1. This D over D minus 1 is the same that appears for spherical averages. Okay. And then this R2 condition is the threshold when we are in this regime. Okay. But then when we are in this regime P greater than 2D, this R becomes P over D. Okay. And this P over D, we can see that it matches, this is where it matches with 2, okay, when we hit this 2D, okay? And also there is this specific with that result in the paper for the dimensions equal to 3 at the P endpoint, okay? This is analogous to Coudan's result. Okay, so for the maximal function, okay, we will have here that we have all this range of boundaries, okay? This is what the maximal function is. And then when we start to make the R smaller, okay, the operator BR gets bigger, okay? And then it gets bigger in the sense that we might not have boundaries all the way up, okay? So then for a fixed R, we only go to R times D, okay? So 1 over RD is the boundary that we have, okay? And this, and then what happens here when we have this equality, R equal to PD, it was left over in the paper, okay? So other than that, all these other conditions we are showing. Okay, and let's quickly look why this condition comes up. Okay, so and typically for variation norm inequalities, I'll sketch this because I don't have much time. But typically for variation norm inequalities, if one really understand the examples for the maximal functions, okay, then variation norms, we need to put many copies of the same example. That's a little bit the idea. Because we are going to have to be taking differences between averages. So I want to put many copies, but with alternating signs, so that these guys, they don't cancel. And then I involve this capital L parameter and the R parameter, I involve the R parameter through the capital N, okay? And then it becomes a constraint in my inequalities. So let's see, for instance, this I equal to PD constraint. So there was one. This is analogous with delta R1. Okay, it's an example that already show up. Okay, it's an important example. It show up when I was getting concentric circles. Okay, but there was another. It can be also put in another fashion where it didn't show up. That is that if I have here, if I just look at the neighborhood of the origin of scale delta, then if I take, I can always land here, right? Okay. Does that make sense what I'm saying? I can always take for each of these points a spherical average, and then my sphere is going to land in the support of this neighborhood if I take this function. F is like this function is. And so I always have then like A1 of F delta. This is 1 if X is more than delta 1000. Okay. So if I were to look at an equality like this, where S here is the maximal function, then I get factor 1 here, but then I get the support of the measure, which is delta over P, but then F is only the width, right? So you can see that for P equal infinity, this example doesn't give you anything, right? For P equal infinity, okay, we already know it's trivially bounded, but then this example collapses, right? Okay. But now we suspect that we might not have boundaries all the way up to infinity. So this example becomes not relevant, okay? So what we do to verify it is that to make this example relevant is we start putting here more angular, okay? But I take let's say this is red, and this is blue, and this is blue. Okay? So then the red comes with a +1, then blues come with a -1. Okay. So then I take my example, which is going to be -1. We want to index for this by n. Okay. And then I'm going to take here these spherical shells, but they are indexed by n. Okay. And if I do that, and I go, how many is going to be 10 to the -1 until I reach the unit the unit angles, okay, for instance. Okay, so then if I plug my variation into these guys, okay, the one that comes into a positive one is positive, the one that comes into a negative one is negative. So then these differences they never cancel, and they are all contributing. Okay, and if they contribute, then what we pick up is the capital N to the one over R. Okay, that's now then this is my G lambda. And then A G lambda X. This is going to be capital N to the 1 over R is minus 1 over R, okay? And then in the same region. Okay? So then ER, okay? So this is the same, but there's going to be an extra minus 1 over R, but now my G, I fill up the whole annulus. So if I fill up the whole annulus, it will be on this one. Okay, so you can see R equal to PD is the threshold. Okay, so this is a natural position. Okay, but then it was open what happens at this point. Okay, at this point you can see there's a strict inequality, but this example doesn't rule out what would happen at the end. Okay, and a couple of years ago, a couple of years, no, 4 years, together with Richard Oberlin, Luth, which is here today, Andreas, and Siger and Betsy Stovall, okay, we managed to, in dimension 3 and higher, so we didn't manage to the dimensional 2 case, then the variation at that endpoint R is then P over D, okay? This is loaded from LP 1 to LP to the field. So it's restricted with, okay? Okay. So here, this restricted with type, 5 minutes. This restricted with type condition comes from applying Bourgain's interpolation trick. Okay, and I don't know if some people are familiar with it or not, but typically is that you have one estimate at some point which is has some geometric decay, another one that has geometric growth, and then the point in which they meet, it gives you a restricted with type inequality. Okay, with Bourgain's interpolation and so so we need is to obtain estimates that just barely fail to be summable, right? In a way. Okay. Okay. So the way we do that, okay. Well, there's a typical split when one study is ordered, which is to split that into long or dynamic variations and into short variations, okay? And where the long means that here we take this variation from inequality, but we take our set E to be power of 4, negative powers, okay? So it's like the lacunary spherical maximal function, but we replace the maximal function by a variation, no? Okay. So for this object, already one can improve the range of P boundedness and so on. So one can improve it to here, of course, I'm missing the right, which is the relevant. Yes. So for these guys, already one can do like in the lacunary case, improve LP boundedness for all P greater than 1. And here is where the conditional equal to 2 comes from this global. In this B short variation, what it is within those intervals, we take usual variation, but we only take it within those. And then we put all the scales together. Okay, so we are short. In this operator, where the variation is restricted here to intervals we have to k to the k plus one, and then we put all the scales together. Okay, in detail accounts. Okay. So initial variations are the one that restrict the peak ranges. Okay, here is where the peak conditions come. Okay, fine. So let me just sketch that how does one treat this short variation. It's the only one that I'm gonna focus on. Okay? And so similarly to when we did the proof of the Stein maximal function, that we try to replace the supremum by an integral, right? In dimensions here are higher when the p was greater than 2, right? And here there's an equivalent of that fundamental theorem of calculus. You can run that fundamental theorem of calculus from the argument, okay, but just the latitude variation, no? Okay, and then there is some of them. That tells us, okay, I'm just going to take one piece and I'm going to think is the case between 1 and 2. Okay? And hopefully we can put them together later on, which is going to be the main difficulty for endpoint estimates. Okay, so in this version tells me I can replace. If I just look at the frequency projection and I'm just looking at the scale 1 variations, then if I'm willing to lose 1 over r power, okay, then the know in the space x and then the r1 with space d. Okay. Okay, and then there is here a crucial a crucial classical estimate, which is a version of the Stein-Thomas inequality. Okay, it's a spherical average. This is the Walker basis square function estimate. So we take the square function. Okay. This is constant. I have no time to explain where these numbers come from. Okay. For integrated one. Okay. Which these are classical estimates, which of course can be interpolated with trivial estimates at an infinity, where an infinity is therefore 1 by 1, right? And so this by interpolation allows me to get R1 same inequality, but now the is now comes with adapting to the R exponent. Just inequality with the infinity. And of course, these inequalities they can rescale so that I have the modes of vortices at 2 to the k, and then here the j would be j minus k, right? So I could put in here 2kt and then j minus k, right? And the inequality rescale at half very C. That's this. Okay, so in this maximal function, we put the scales together. How did we do that? We said, okay, if p is greater than 2, we could run this little weak interpretary argument, right? I don't know if you remember that's how we put the scales together. Because now this inequality is scaled, so if I could take here this sum, okay, in k, and I could just put them together by little Bailey or something like that, then I would be done, right? Okay, but little Bailey is gonna, here I have a little LR norm, right? So in order to be able to pull it down here, I will need that R is greater than B. Okay? Which for the maximal function, that's always okay. That's always, and then this greater than B. Okay, for the maximal function, this is always okay. But now I am willing to do something when the p's can go up to R times D. That's my endpoint. So putting it together through little Peltian projection is too restrictive because I want to go to R times D. So it only gives me one part of the range that I want to establish my equivalence. Okay. So we need some smarter way to put the frequency scales together. Okay? Not the frequency scale, sorry, the dilation scales together. Okay. Okay. What was this H1 argument, for instance? It was about putting these K scales together, which were the dilations, right? And also the lacunary was putting the scales together. So this is, so in here is where we use these Pepperman-Stein charge maximal fraction arguments. Okay. And you can see so if we use the Pepperman-Stein charge maximal function, which is even a function T. It is given by that, and we apply it to our with g of x to be our averages. Okay. So we apply it. X to be only all those scales together. We already here are not already. Then well, we know that the norm of this is controlled by the norm of this, and then if we can prove good bounds for the Char maximal function applied to this, then we are good. Okay. And again, if we now look at what this is, okay, we just apply this with this guy. Then I have here this sum, okay, and I have here minus this average here over the cube of the sum. Okay, so these I can put together by okay, I can put together by triangle inequality these LR norms. Okay, so no inverse triangle inequality. These I can include. So that's the quantity that one wants to estimate in every node. And now there's a here, so we just do the same games that we have been doing the whole week. Okay. We are hoping to use the cancellation at some point. We are hoping to use the bottlenecks that we already know for our operators, right? That is here, this bottlenecks that we already know. We already have some information, right? So let's try to use those things. Huh? And in order to use those things, I need to know when it's smart to use which option. No? So I could, of course, break into scales for my cubes to just start to sort things out. And then here, decide for the cube to be that okay. And then I can do the same here, no? So I could say this sum, where do I want to break it? So I can, if I'm in a cube here, and then then this is not gonna amplify my support too much, right? It's again the same game as before. So here I wanna be able to use the bounds of my operator, okay? Using that is local, my operator, and the fact that it's an operator local is gonna help me to replace this by having little maximal function and so on and so forth. So here we use that is local. Here we are going to use the cancellation. Essentially, this needs to be split into two parts, no? Because if we look at what the L is, and then we have the K here, then we do the same game as any. We introduce an N, so the K, we write it as L plus N, and then one geometric decay in the N variable, and then the limiting case is when the L, when the K is equal to L. So that is the same sort of idea as we gain in the end. So with this I conclude. So I wanted to exemplify that the same theme can be seen from different perspectives.
Are you ready? Any questions?
Can I ask a question?
Yeah.
So what happens in the range between with this argument two, is that sharp?
Argument 2 is sharp, yes.
So is there possible to prove these oscillation norm bounds of two, like the two oscillations? Is that the one?
Okay, I know that there is this jump inequality. Remember that Tommy talked to us about the jump inequality, the oscillation, and the variation. No?
Yeah.
And these jump inequalities, it could be seen like as a weak tag, like the weak space corresponding to the two variation.
Right.
And then in our context, results for r equal to 2, I believe that you guys proved the jump inequalities result. Okay.
Yeah,
But
the two jumps.
The oscillation and
No, I don't think it's ever been worked out,
No.
but I suspect you get two oscillations.
Yeah.
Estimates now, when you're dealing with two oscillations, the thing is, the ultimate thing is to prove uniformity. Is that two oscillations defined the same with respect to a sequence of a fixed length. So there's two parameters, the length of the sequence and the sequence itself. So and then you'd like to show you get a value uniform in both.
right.
Right, this is yeah. And I suspect it's true.
Yeah, well, what about D plus 2? So this breaks down, but we still expect the result. I'm talking about the regime that you have.
Oh, so this breaks down because we have a condition coming from here that so in order to apply, because when we try to apply the Lorentz interpolation trick, that we need to have one good estimate at in one side of P and the other bad estimate on the other side of P. And the good estimate only holds for dimension 3 and higher, but I guess it's because of these inequalities that we are using from cycle.
Yes, so you can use. Is it not possible to use what some of the inequalities?
So I think it did, but I'm not sure if it was helpful because we use the logarithm inequality data for the LPOQ bounds that are included in the paper as well. And I don't think they were giving the right here.
Any other comments? I got a quick question. In the result by you overview and the article.
Yeah.
You have restricted with time.
Yeah.
Then is this optimal in the sense of?
No, it could be with type, for instance. It's open how much we can improve it. Yeah. So it's not only open dimension 2, it's also open what is actually the right inequalities, because the example I presented is not fully other options. And I don't know how to improve an example with logs or whatever that's can roll out with type.
questions? If not, then let us thank David for all these lectures.